Hey guys, so if you are here, then it is because I either emailed you about retaking the Newton's second law test, or if you would like to just sign up and take it on your own accord, then that is being offered today, or sorry, tomorrow when you view this. Yeah, and it's going to be between 1 p.m. and 2 p.m. on formative. All right. So I thought I could just go over kind of what that test was about and show you guys how to work a few free body diagram problems. So we might have to get a little creative with the format here. All right, I'm going to go through this a little quickly just because it's material we've already covered before, and it's kind of just a reminder just since it's been a while. I'd prefer you guys take this before we go on spring break, if only so that it's still kind of fresh in your mind, okay? So first off, the difference between acceleration and velocity. Remember that velocity is just what we talk about whenever we're talking about speed, in general, speed with a direction. And acceleration is a change in velocity. It's delta V over time. So it's a change in velocity over time. Acceleration can be three things, right? It can be speeding up. Oh man, I thought maybe I would get my highlighter. Okay, it can be speeding up, it can be slowing down, or changing direction. So if you're doing either of these three things, then you are accelerating. Next thing, so on Newton's first law test, we looked a little at position versus time graphs. Well, Newton's second law is a little bit about velocity versus time graph. So just a couple of things. Anytime we have a difference in velocity, so anytime this is increasing a lot or decreasing a lot, so we see it's accelerating slowly here, accelerating quickly. However, this is all acceleration, right? Because velocity is on this side of the graph, velocity is on this side, and time is down here. So here's what I'm saying. As time goes on, my speed is changing. It's changing a little bit this time. The slope isn't very steep, whereas the slope is very, very steep here. So I'm speeding up a little bit, and then I'm speeding up very, very fast. Right here is steady speed, and this is where it's a little bit different from position versus time graphs. So where it sort of levels off here, that tells me that I'm going at a constant velocity. You might think of this as cruise control in your car. Or if you've ever ridden your bike and there came a point where you were coasting and you could just not pedal at all, then you were moving probably at a constant speed. So you're still moving, and that's kind of, I think, the hard thing to remember here is that you're still moving, you're not getting any faster, you're not getting any slower. Here we have a sharp decrease. So this is deceleration, where it's just still a type of acceleration. And then finally, the only point on a velocity versus time graph in which you are stopped completely at a standstill is along this line. So look at what I'm saying here. I'm saying velocity is 0. My speed is 0. So of course I'm not moving. But time is still passing. So time is passing, but I'm stopped. And then don't worry about this stuff yet. This gets a little bit more complicated as you get into higher level science classes. Okay. So these are the graphs we're used to. These are the graphs on this test. Move me out of the way. Slope is the acceleration now. It's not velocity. You're either speeding up or you're slowing down, and how steep that slope is tells you if you're doing this very quickly or not. A flat line means a constant velocity, whereas over here it meant an object at rest. And then lines cannot go straight up or down. And if it's at rest, then it's on the actual x-axis. Okay. We didn't really do too many of those. All right, Newton's actual laws. We'll go a little quickly here. Okay, quick reminder of what a force is. A force's simplest definition is that it is a push or pull on an object. And we've talked about a few different types of forces. We talked about gravitational force. It's the force that planets or other large bodies in the solar system put upon the things interacting with them because they have such large masses. So the Earth has a gravitational field and it pulls us closer to it. There's also these contact forces. So we're going to ignore electromagnetism for now because we just had like a whole unit on it. Okay. So applied force is when you actually physically push or pull something. So this is talking about sports, talking about construction, talking about moving equipment. This is all applied. A spring force is any force where you have some kind of elasticity to it. We probably won't deal with that one very much. Okay. Drag force is kind of another word for air resistance. We talked a little bit more about air resistance. Air resistance is like friction, but in the air. Which brings us to the one you have to draw the most often, and is honestly probably hardest for students to remember, is a frictional force. So we have friction anytime molecules between two objects are kind of sliding or maybe rubbing or in contact with each other, and they typically are going to slow down or stop a movement. An object in motion does like to stay in motion unless there's some friction there that stops it. The only times we're not going to have a friction force is if we are on just like the most beautifully iced, it just got Zambini'd, you are just like ready to hit it on with your ice skates surface, or if you're floating through space. If you have not been in either of those scenarios, then there is a frictional force, but friction increases as you get into rougher surfaces. So for instance, I use the example in class of which one does a Hot Wheels roll the best on? Probably something like your kitchen tile and maybe not your carpet, right? Carpet will have more friction. It will slow it down more. Okay. We won't go into Isaac Newton today. Newton's first law is not on this test. All right, balanced and unbalanced. Here's what you need to know. A balanced force means that the net force is 0. The forces acting on that object are equal. This happens for 2 reasons. So there are 2 cases in which you will have a balanced force. They are one, you are completely still, you're at rest. And 2, you're moving at a constant velocity. If you're moving at a steady speed, then you have a balanced force. An unbalanced force, they say, is when a net force is greater than 0. But an easy way to remember this is an unbalanced force is acceleration. So if I had you circle, here, let's go back just a second. Didn't realize how far back. Okay, there we go. If I had you circle on this graph where a balanced force was, then the only places you would circle would be when it was moving at a steady speed and when it was completely stopped. Everything else would be an unbalanced force. See how it's accelerating slowly, accelerating quickly, it's slowing down, it's moving in an opposite direction. It doesn't matter. Those are all accelerations, and therefore they are all unbalanced forces. Okay. Alrighty, moving right. Oh no, we don't want the video. Okay. All right, this is a great graphic actually. And in fact, if you want to pause the video here and just make a little note of that, then I think that would really help you guys learn to study. So forces are balanced if objects are at rest. Objects in motion, acceleration is 0, it stays at rest. Acceleration is 0, it stays in motion. So constant velocity or just completely stopped. All right, Newton's second law is what you came here for. Triangle, also really, really good. And hold on for just a second. Let's see if I can get my little markers. Boom. Let's make it pink for fun. Okay, I'm going to draw a multiplication symbol. Dot for dividing, dot for dividing. Move myself down here. Oh, of course. Will they stay? Ah, they don't stay. Okay. Sorry about that. All right, so Newton's second law is a force equals a mass times an acceleration. Don't forget that we measure forces in newtons we measure masses in kilograms. 1 kilogram's about 2.2 pounds. So however much you weigh, just kind of slash it in half, and that's roughly what you weigh in kilograms, okay? So a 100-pound person weighs about 50 kilograms. For being more honest, it's probably about 40, but somewhere in between there. And then acceleration is meters per second squared. The square does not mean that you square the number. Do not square the number. It doesn't do anything. It just stays with the seconds. Don't worry about why. It stays with the seconds. Okay? But this little 2 here does tell you if you're talking about acceleration or velocity. Remember, velocity is meters per second. So if it says meters per second, then I'm talking about velocity. And if it says meters per second squared with the little 2, I'm talking about acceleration. Okay? The triangle is an excellent way to sort of keep track of what goes on top. So force equals mass times an acceleration. So I talked about if I cover up here acceleration, if I'm solving for acceleration, then acceleration is a force divided by mass. So this lets you sort of keep track of what goes in the numerator and in the denominator. Okay, I'm going to take a small water break. Okay. Let's see. This is where I'd watch you guys' video. And okay, there's different types of friction. Gravity. Oh, actually, this is important. Okay. I'm not going to play this video, but one of the important things to remember about Newton's second law is that when we talk about weight versus mass, so mass is how many atoms make you up. It's not something that really changes, okay? But weight is the pull of gravity on your body. It's typically represented as your mass in kilograms multiplied by the force of gravity on Earth. Now, for most of us, we've only ever experienced gravity on Earth, and we are probably never going to experience gravity in any other scenario. So talking about weight and mass in everyday conversation means that we're sort of talking about the same thing. Our weight is our mass. But if you have ever gone swimming, then you know that sometimes your weight can feel different, right? So if we're underwater, if we're swimming around, then our weight is sort of displaced and you might feel lighter. You might be able to maybe pick up a person you normally couldn't. Maybe you can sort of propel your body further, okay? Those things are because your weight is being displaced, but the actual amount of atoms that make you up hasn't changed. You still have the same number as when you entered the pool and when you exit the pool. So the only thing that's really different is just that pull of gravity upon you. Not that gravity changes when you're in the pool. It's just your weight's displaced, okay? All right, so all objects on Earth are going to have the same acceleration due to gravity. The thing that changes how fast objects fall is actually due to air resistance, but we have the same amount going down each time. That happens at a constant rate of 10 meters per second squared. Okay, so your weight on other planets. If you weighed, let's see, do they not have it here? Yeah, there we go. If you weighed 100 pounds on Earth, then this is what you would weigh on other planets, and that is because of the different accelerations due to gravity on those planets. And that acceleration of gravity is caused by how massive those planets are. So Jupiter is a more massive planet than Earth, therefore you weigh more on Jupiter. You weigh less on the moon because the moon is only a tenth of the size of Earth, and therefore you have less weight on that planet. Now you would have the same mass on all of these planets. You wouldn't all of a sudden gain or lose an arm, but you would feel different. Okay, and with that, we are going to switch to our last thing, which is doing a free body diagram. Okay, so I'm actually going to switch this off of me real quick. Let's plug this in. Okay, sorry about that. So what I would like you to do, if you're at home, you're watching this, then please go ahead and take out a piece of paper and sort of follow along with free body diagrams. Free body diagrams are pretty difficult actually for people to get, and it really helps just to do as much practice as possible. So do some of these with me, and then hopefully that'll help out. So let's switch to this and get out of this window. Switch on my ladybug. Alrighty. Okay. Let's get a dark color that will show off. Okay, hopefully you can see that. Okay, so what I'm going to do now is walk you guys through a few free body diagrams and what they're going to represent. So first, I'm going to draw my force, the forces that I'm allowed to use, okay? Let me just turn this down a little bit and actually, okay. There we go. So most importantly is to make yourself a list of the forces that you can use. Those include forces, right? Okay, they include big F, little g, so that's how we're going to represent it. This one is gravity. There is also Fn, that's normal force. There's F of T, which stands for tension. Fa stands for applied. And finally, FAIR is going to stand for air resistance. And I know I just said finally, but I was just kidding. We've got one more. F of little f equals friction. Okay, so let's do a couple examples. So in problem 1, let's sketch out problem 1 more quick. In problem 1, I am going to do a free body diagram of my cup on my table. My cup is at a standstill, so it's not moving at all. Okay, here is my cup. You're welcome to do a different object. So next thing, I'm going to draw my arrows, my forces acting upon my object. And I'm going to use these as my example, okay? And actually, let's go ahead and get rid of tension. I don't think we use that until later grades. I apologize. Okay, so we've got these 5 to choose from. So the first force that is always acting on your objects, if you are on this planet, is gravity. And gravity pulls it downward. So whenever you're drawing your free body diagrams, you want to draw the arrow in the direction that the force is going. So gravity goes downwards. I'm drawing my arrow downwards. Okay? Now, for each force, there has to be an opposite force, right? Our opposite force, if we are on a surface, so this is going to be my desk right here. So the desk is supporting the cup. The desk is making sure that the cup does not fall to the ground. So the desk exerts a force on the cup as well, and that is called F of N, normal force. So normal force is the force that is exerted on a surface, okay? F of G pulls down. F of N goes upward. Surfaces point upward. Now, this cup is not moving, right? So this is all I have to write in my drawing. But let's say all of a sudden that my cat, this is a bad cat. Yeah, it's not great. It's not great. Okay. My cat, let me give it a little nose. Okay. Jumps on my desk and decides to knock my cup off. I realize that now the cat is the size of the cup. I have regrets about my scaling, but that's okay. So my cat has decided to knock off my cup, and it is going to hit the cup, knock it off the table. So let's look at this. Then, if the cup is going to accelerate, so the cat is going to apply a force. It's going to push the cup this way. Oh, one other thing I forgot to mention. Whenever you're drawing free body diagrams, please make sure that your arrows connect to your object. You are diagramming the forces on the cup, not on anything else. If I wanted to, I could also draw the forces acting upon the desk, and I could also draw the forces acting upon the cat. But I know I'm talking about the cup because that's where all the arrows are coming from. So sometimes I see things like this from you guys, and like it's over here, and I don't know what those forces mean. Okay. All right. So the cat knocks the cup. This is the applied force. Force applied up here. Force applied. Okay. However, there is a little bit of friction between the table and the cup. So remember, there is friction unless it's very icy or space. So there's friction between surfaces. In this case, this force of friction is going to go this way. It's going to go in the opposite direction of the movement. So here's big F, little f. All right, now let's say my cat manages to knock the cup off the table. So I'm going to draw the table here. Here's the cup falling onto the ground. Let's say ground's all the way down here. For some reason, this is a really weirdly tall desk. All right, so as my cup falls, there's a couple forces happening. There is now force of gravity pulling downward, but there is also a different force. So notice that the cup is no longer on a surface. It's not on the desk and it's not on the ground yet, but there's some force that slows it down just a little bit. Because it has some surface area, there is the force of AIR, or air resistance, that is kind of slowing down the cup as it falls. All right, let's look at one more example. Okay, so I am going to switch out pins real quick. I want to. Okay, and quick reminder of my forces cheat sheet. I have force of gravity, force normal, force air resistance, force applied, and I have force of friction. Okay. All right, let's do a person who is in free fall. So here is my person. They have jumped out of a plane. Here's the plane. Okay, and here's my person. I'm gonna give them a little backpack. So they're going skydiving. They are right now plummeting to the earth, but it is all okay. They are having a good time. They have just not deployed their parachute quite yet. Okay, so as my person falls, the only force acting upon them is the force of gravity. And then they have a little bit of air resistance, F, air. So remember, you're always going to have gravity pointing downwards, but the one pointing in the opposite direction will either be normal force or air resistance, okay? Now for air resistance, This is smaller than gravity. Notice how this arrow is not as big. So our arrows show us two different things: the direction of the force, but also the size of force. So how large the force is. So in this case, the acceleration of my person due to gravity is much larger than the acceleration in the opposite direction. Okay. Let's see what else. Okay, so they continue falling and they decide to deploy their parachute. So now I'm gonna draw the same person underneath, backpack, arms, legs. Okay, and here is their parachute. All right, clearly you guys miss me for my artistic abilities. So my person is now still falling, right? So the arrow that's going to be larger now is still gravity. They're still accelerating in this direction, okay? But my air resistance is now larger. In fact, it's large enough that I am slowing down. So I'm still going faster this way, but I'm not going quite as fast this way. That acceleration from 10 meters per second squared, which means I fall an extra 10 meters every single second, is now maybe reduced. After a while, this force, this air resistance force, is going to equal the force of gravity. And then finally, they're going to be the same length. So if I was to draw it over here on like a box, then I'd have force of gravity and force of air resistance. If these are the same size, then I have a balanced force, which, as you guys remember, means one of two things. It's either at rest or a constant velocity. So a person falling, right, they can't be at rest. They're falling. But they can move with a constant velocity. And this is how people who go skydiving stay safe. Eventually, the air resistance of the parachute is equal to the force of gravity upon them. And these are going to balance each other out. Okay? That is your review of forces. And please let me know if you have any questions about this video or if you would like to talk to me before you take your test.